Hi, everybody. Good that you have all been able to join this morning, this afternoon, this evening, wherever you are in the world right now. Today, what we're going to be talking about for the next hour or so is it's a little bit different to what has been covered in the previous couple of weeks. There's actually some more statistics in it this time. You may or may not be pleased to know, I don't know, depending on your point of view. We're going to talk about the concept of statistical estimation. And we're going to start out very simply, a quick recap through things that I'm pretty sure you will have all covered before in introductions to statistics, just to get everybody up, nice, gentle opening of recapping how we present results from data, and then starting to think a little bit more about the process by which we get those results, what we mean when we talk about estimation and standard error and confidence intervals, and talking about these very key concepts of precision and variability and how to represent those concepts when we present our results from our data analysis. And also at the end, we're going to talk a little bit about implications for disaggregating data. So I'm going to set up an example, which I'm going to keep referring back to over the course of the next hour. It's sort of a made-up example, but hopefully it's easy enough for you all to relate to your own particular bits of work. So I am today going to be the owner of an organization which purchases oranges from 1,000 farmers. 1,000 farmers because I'm very keen on having nice round numbers. I don't like having awkward sample sizes. So I've got 1,000 farmers. I am a shady businessman who is able to keep records on all farmers who are part of my organization. So I know what their name is, I know their age, I know their gender, I know how many oranges they've been selling to me, I know whether they've been taking part in my orange growing training sessions, and so on. So I have data on all of my farmers because I am able to collect that data because I own this organization. And I would like to investigate my data to see what I can find out about the farmers who I am working with. So I have built myself a little toy. Hopefully you are seeing the right screen. Yes, good. So I have got here a data set about all of my farmers. And as a small aside, whenever we talk about wanting to have clean data, this is the kind of format of data that we would be looking for. So I've got my variable names at the top of my data set. I've got a farmer ID, column for farmer ID, it's just a number, a unique identifier for each farmer. I've got a column called training, which tells me, did they take part in my training sessions, yes or no? It's consistent if it says yes, it always says yes in the same way, with a capital Y. It never says just the letter Y, it never says yes with a small y, it never says training or I went on training, it's consistently written in. This is something you will get if you use a digital data collection tool like Carlos was demonstrating recently. It's not necessarily something you will get if you enter the data by hand. So you have to think about these things if you do end up entering the data by hand. Anyway, continue. I've got a column called gender. I've got some female farmers and some male farmers. I've got a column called age, which has got the age of the farmer. And I've got a column called income, which is how much income they got from selling oranges to me as my shady orange farmer. If I go down, it tells me here I've got 1,000 entries, 1,000 farmers. I can keep scrolling through this data set for hours and hours and hours, just looking at the raw data. But it's going to be very hard just looking at the raw data to try and work anything out about the overall summary of who these farmers are, what's the breakdown of gender, what's the breakdown of age, how much income are they getting. And so this is why we do summary statistics. So let me move over here. So if we are trying to summarize how many female farmers, how many male farmers, very, very simple, we calculate a percentage. when we have a variable like gender or training, this is really easy to create estimates or summaries. We can see that of my 1,000 farmers, 593 were female, which means 59% of them were female, or 59.3% if we really want to be precise and specific. And if I want to present this graphically, I can do a little bar chart and say, oh yeah, my female block goes up to 59%, my male block goes up to 41%. We can do something very similar for training, and I can say, oh, how many of my farmers have been attending my training? In this case, I can see most of them went on my training course. 839 of my farmers went on my training course, which is 84%. So when we are calculating summaries of these categorical variables, it's pretty straightforward in terms of the numbers that we want to calculate to begin with. We get frequencies, we get percentages. If we want to display it graphically, we do a bar chart. I'm sure I'm not saying anything here that you haven't learned at school and at university and whatever. Very straightforward to begin with. Gets more interesting now when we start to think about other variables like, for example, age. So with the age, I can calculate a mean average. So the average that we have here is 44.8. That doesn't tell us that much about the distribution of age in our data set. We can calculate lots and lots of different statistics about a numerical variable. Here I've put a few. I've got standard deviation, median, minimum, maximum, 5th percentile, 25th percentile, 75th percentile, 95th percentile. I can keep going. I can do things like kurtosis and skewness and all these other kind of statistics that you sometimes see, because there's lots of different things to try to understand when we're trying to understand what's going on with age. And just presenting the average alone doesn't tell us that much information about the distribution of age. So here, on average, farmers were 44.8 years old, but we've got one farmer who was 12 years old and another farmer who was 81 years old. And when we are trying to summarize this variability, minimum and maximum, they tend to be the extreme cases. They're very rarely that useful in isolation, because they will tell us, okay, we have one really interesting case here of a 12-year-old, one really interesting case here of an 81-year-old. But in terms of a generality and a commonality and some patterns, the minimum and the maximum don't tell us too much, which is why when we're trying to, or when I am trying to understand a numerical variable, all of these numbers, there's too many numbers to consider. Looking at a picture is much easier. Looking at a graphical representation is much easier for me to understand the variability and the spread and the kind of distribution of farmers that we've got. So here we've got a histogram. We can see most of our farmers are in this sort of range here, around 30, 35, up to around 60. We've got quite a lot of farmers in that age range there. We've got a few farmers in their 20s, a few, maybe one or two slightly younger than that, one or two into their 70s. Even better than a histogram sometimes is this thing here called a box plot. If you haven't seen a box plot before, these are very, very, very useful summaries to understand the spread of the data. This takes all of our data values and does another way of representing them graphically. We can see here, here's our 12-year-old farmer at the bottom, here's our 81-year-old farmer at the top, and it partitions the rest of our farmers by age and says, this black line in the middle, this is our median. Half the values are higher, half the values are lower. This one here is what we call our lower quartile. 1/4 of the values here are lower, 3/4 are higher. This is our upper quartile. 1/4 is higher, 3/4 are lower. We're getting an idea of the distribution of ages from our farmers, not just saying, okay, the average is 45. This becomes much more important when we start looking at a variable which is a bit less well behaved. So if we look at income, so this is the amount of oranges that I am buying off these farmers. Most of our farmers here are getting quite low income. We've got lots and lots of farmers here getting around between zero, a bit more than zero, because I think the lowest is about 70, up to about 7,000, 8,000. But our mean here is 10,000 units of currency in whatever country I'm working in. So our mean is way, way up here. Most of our farmers are getting an income which is considerably lower than our mean. And our maximum is all the way up here at 80,680 units of income. Well more than sort of 10 times the amount which these farmers over here are earning, which is where most of my farmers are in this distribution. So we can do a histogram which shows this skewed distribution, or we can do a box plot which would also show this skewed distribution, showing we've got a really high density of points down here at the low values, and then increasingly few farmers up here at the higher values. Seeing either this histogram or this box plot, I would be able to understand much more clearly the spread and the variability in the data, rather than going through the mean and the standard deviation and the median and the minimum and the maximum. Looking at all these numbers together, it would take me a long time to work out what is going on. Looking at either of these pictures, I can work out what's going on almost immediately. So graphically representing your data is a much better way of displaying variability than presenting hundreds and hundreds and hundreds of summary statistics when we're dealing with numerical variables particularly. If we go back to gender, I can read this bar chart, I can read these numbers, they make sense. Converting it to a percentage is usually useful. We don't always have a nice exactly 1,000 farmers to work with. In this case we do, which makes it easy to read the numbers, but usually converting to a percentage is a good idea. But whenever we have a distribution, we want to try and understand what's going on. Okay, so one more thing just to pull out. I've pulled out this number here, which is the standard deviation. This is a number which is quantifying how much variability there is in the data. This is a number, again, by itself, it's not that useful. It takes a little bit of thinking to work out, why are we calculating this number? What does it mean? How can I interpret it? As a little trick, if you have some data which looks like this, it's roughly symmetrical. So here we have what we would call a skewed set of data. Here we would have what we call a symmetrical set of data, because it goes up and goes down again. When we have this kind of symmetrical distribution of data, the standard deviation, if we multiply that number by 2 and add it to the mean and take it away from the mean, then that gives us the range in which roughly 95% of our data can be found. So in this case, if we multiply this by 2, we get 20.8. And if we add our 20.8 onto our 44 and take it away from our 44, so 20.8 plus 44 is about 67, which is somewhere around here. And we can see, yeah, most of our data is less than 67. We take that away from our 44.8, that gives us about 24.1. That's somewhere over here. Yeah, most of our data is more than that. So that's my little trick for trying to interpret what that means in real terms. Because you will usually see this number quoted, and I always have to do a lot of mental gymnastics to work out, okay, is this a big number? Is this a small number? What does that mean about the spread? That trick doesn't work when you have a skewed distribution. Here, our standard deviation is about 10,000. We can still calculate the standard deviation of a skewed distribution. But if we multiply that by 2, take it away from the mean, we then saying that we think most of our data is more than negative 10,000 sales income from oranges. And if we're just talking about sales income, we haven't got a very sensible statistic if we're saying that negative 10,000 is your income, not your profit, your income. So it doesn't work in cases where you've got this kind of skewed distribution. Okay, so this is all very straightforward. Hopefully things that you have all learnt before. or recapping things that you've all learnt before. But sadly, we are very rarely in the situation where that is sufficient. In this case, I was the shadowy owner of the organization. I was able to look at all 1,000 of my farmers. I forgot I had this recap slide, but yes, just to recap, summarizing averages or commonality, so means, medians, frequencies, percentages, these can be well understood as numbers. Trying to summarize the variability and distribution through numbers is usually better through a graph than through lots of these complicated statistics. So you've got variance and kurtosis and skewness and standard deviation, all these numbers which are quite hard to interpret by themselves, whereas a simple graph can tell the whole story. Things that are often more useful are those percentile values that I quoted before, saying, okay, the 5th percentile, the 25th percentile, the 95th percentile, you need to quote all of them to be able to get an idea of the spread, but those are at least telling you a little bit more about how the distribution works. But again, a graph does the whole job. So let's maybe now come up with perhaps a more realistic example. I am not a shady owner of a big orange organization. I am a researcher, and I am evaluating an orange organization. And this happens to be the same orange organization that I mentioned before. So instead of a shadowy figure, I am a person looking at oranges with a clipboard and a hat. And I want to understand what's happening with this organization. My objectives are almost exactly the same as before. I want to know how much is being sold, what the gender breakdown is, whether they're attending the training sessions. So I want to understand what's happening in this organization. But I do not have access to this wonderful database of 1,000 farmers. And I don't have the time or money to be able to do interviews with 1,000 farmers. So instead, I am going to speak to some of the farmers. And again, because I like nice round numbers, I'm going to start out by speaking to 100 of the farmers. So let's go back and let's see what happens now. So I am going to take a sample of 100 farmers from out of the 1,000. So if I go back to the data, I've set this up so I can say, okay, I would like to take a sample of 100. And the computer has now randomly selected 100 farmers to be part of my survey. Hypothetically, I am now going to go through these IDs. You can see I've got 100 in here and speak to farmer 15, 26, 29, 32, 37, 55, and so on. These are the 100 farmers that I have randomly chosen to be part of my survey. If I now look at the summary, from these 100 farmers, I found that 63 were female and 37 were male. So my percentage of farmers who were female was 63%. But it was completely random which 100 farmers ended up in my survey. I can do another survey. This time, I've now got 60 farmers who are female and 40 farmers who are male. So instead of having 63% female, I've now got 60% female. This was a completely different set of 100 farmers who just happened to be in my survey this time. I can do it again. This time, I've now got 67 farmers in my survey and 33 who are female and 33 male farmers. Every time, I don't get exactly the same result, even though I am looking at the same objective each time. I'm doing the same process each time of selecting 100 farmers from the sample of 1,000 farmers and estimating what percentage of the farmers are female. I can keep going again. Next time, maybe I get 67 again. It didn't change. That time I got 53. Huge drop down. So we will have variability in the results from one survey to another survey. In reality, we only get to do this survey once. We don't know if we are in this situation here where we got 53%, which was quite different to our previous results, or we don't know if we're in this situation here where we get 62%. So I've plotted on here. Here we go. Each point along here is a different survey. Each point on the y-axis here is a different estimate that we have got from that survey. So I'm going to just click lots and lots and lots and lots and lots and lots and lots of times. So I have just done 30 surveys. Each time I have sampled 100 farmers, and each time I have estimated what percentage of those farmers are female. In some of the surveys, I was getting about 53%. In one of them, I got only 50%. In another survey, I got 71% as my estimate. If you remember from before, the real answer, when I had all 1,000 farmers, when I was the shady businessman rather than the slightly nerdy researcher, the real answer was here, it was about 59%. So sometime I'm getting an overestimate, sometime I'm getting an underestimate, sometimes I'm getting it exactly right. But as I said before, we only get to do this process once. We don't get to do this process 30 times. So we don't know if we've got it right or if we've got it wrong or if we're over or if we're under. So when we present our estimates, what we like to do is we like to clarify what is the level of uncertainty in these estimates. So this often gets called, what is the margin of error in this estimate? The statistical terminology would be a confidence interval. And if I just go back here, we can calculate for each of our estimate, if we just start with survey 1 for now, what we call the 95% confidence interval. What this means is if we were to do 100 surveys, in 95 of those 100 surveys, we think that the real value of the mean, real value of the percentage female is within that confidence interval. If we were to do 100 surveys, each survey we calculated a 95% confidence interval. Of those 100 surveys, the real value is within the 95% confidence interval 95 times out of the 100. So here it's saying this is the range of values in which we expect the true value to lie. We pick 95% because we like round numbers as statisticians. Someone decided that 95% was a good number one day, and that's about it. You could have a 99% confidence interval, you could have a 90% confidence interval, you could have a 0% confidence interval. It would be stupid. If you wanted a 100% confidence interval, which sometimes people ask for, that would go from, well, in this case with a percentage, it would go from 0 to 100. We are 100% confident that the percentage of female farmers in the orange organization is more than 0% and less than 100%. For age, if you wanted a 100% confidence interval, it would go from 0 to infinity. So we never calculate a 100% confidence interval. 95% is sort of a high number, which is sufficiently high. Just to demonstrate this, if I go back, and now I've done 100 surveys. And in each of my 100 surveys, I have calculated my 95% confidence interval. Hopefully, if I scroll along, 95 of these intervals will be including the real value of the percentage female. And there should only be 5 where the value is missed. So we see here one time we got an overestimate there, another time we got an overestimate there, there's an underestimate there, there's an overestimate there, and there's an underestimate there. And yeah, I think the computer has accurately given me 5 times out of my 100 where we've missed it. It could have been 4, it could have been 6. There's an element of randomness in there, but it got it right this time. But every single one of my other 95 surveys, when we said, okay, what range of values do we think the real mean value could lie in, it got it right. But let's think a little bit more carefully about this interval. What is this actually telling us here? If we go back to number 1, the lower limit here is, if I scroll on it there, you've got to get it exactly the right place. The lower limit there is 54%. The upper limit is 72%. So this is saying from this first survey, we think the possible range of values in which the percentage of female farmers in my organization could lie is between 53.9% and 72%. This is quite a big range of numbers. This is plus or minus about 10% from the estimate itself. This is what we call precision. This is quite an imprecise estimate because we're not very confident with our guess of 63%. We're saying it could be quite a bit more than that, up to 72%. It could be quite a bit less than that, down to 53%. Let's, if I tick this box, it just narrows it in a little bit. It shows it on the range of 0 to 100. But if I now increase my sample size, let's say I've suddenly found some budget out of nowhere, and I'm now able to get 500, oh, not 490, 500, 500 farmers in my survey instead of 100 farmers in my survey. And you'll see we're much, much more consistent here about where our estimates are lying. We're not seeing anything in the 70s or anything in the 40s. Here, this time we got about 61, there we got 61, there we got 57. So we're either getting high 50s or low 60s more or less every single time. And our confidence intervals are really, really small now. It's now down to between about 59% and 65% for our first survey. And here between about 55% and 61% for our 75th survey. Again, we only get to do this once, so we don't get to see this. But our confidence interval has shot right down. We're much more precise with our estimate for what we think the true percentage of female farmers in our organization is. If we go to the other extreme, let's take a sample size of not 0, 0 is a little bit too extreme. Let's take a sample size of 10. If we take a sample size of 10, it's starting to get confused with some of the calculations because it's huge, great confidence intervals. Some of the time it can't calculate it because it's not enough data to be able to calculate it. It's giving estimates of more than 100% because there's just not enough data to be confident where our estimates are lying. We're saying, even in the cases where we can calculate it, between 5% and 75% of our farmers are female. This is clearly not a very good estimate. Trying to work out where the sweet spot for precision is a very difficult thing to do. We can calculate, say, okay, we want to be perfectly precise. We want to have all the farmers survey our entire population. If we do 100 surveys of all 1,000 farmers, we get exactly the same result every single time. We get the right result every single time. But it's a bit of a waste of money to speak to all 1,000 farmers. If we speak to only 500 farmers, we get a pretty good estimate every single time. Our margin of error is not so big. We think, okay, between 59 and 64% of our farmers are female. That's a relatively easy, low level of precision. What if we go to 250? Oh, now we're a bit less precise. Sorry, 250. My fingers aren't precise enough. Here, okay, this time it's about plus or minus 5% when we're at around a sample of 250 here. Is that an acceptable margin of error to give when we're presenting our results? Maybe it is, maybe it isn't. So there's no right answer to where we should be drawing the line in terms of determining what our sample size should be. It's a relatively subjective process for working out what is an acceptable margin of error. This process is exactly the same theoretically, whether we're dealing with percentage of female farmers, whether we're dealing with age of farmers, whether we're dealing with income from farmers, which has a different sort of distribution. Every time we can calculate an estimate, we can calculate a confidence interval around that estimate. With something like sales income, which is a variable which we saw before the distribution was skewed, there was a lot of variability in there. It went all the way from about 70 units of currency to 80,000 units of currency. This is going to have very imprecise estimates because there are two things which go into the calculation of the confidence interval, which is the sample size and the underlying variability in that particular variable that we are looking at. So with income, even with 250 farmers, if we're looking at the estimate of mean income, we're saying this could go between 8,500 units of income up to 10,500 units of income. With a sample size of 100, which wasn't too bad for gender, it's even worse. It's now going sort of plus or minus 2,000 units of income when we're trying to get our estimates, which I am telling you is a large amount of variability in the country which I live in, which is a non-specific country, because I don't want to pick any particular real units because I don't really know how much money you can make from selling oranges. It could be a lot, it could not be not a lot, I don't really know. But again, even if we get all the way to 1,000, we still get exactly the same result every time because we've sampled the entire population. So when we've looked at the whole population, we are still able to get the same result every single time in our estimate. This has a lot of variability within income. If we go back, there's a whole range of values it can take. The variability is high regardless of the sample size that we have. But if we have a large sample size, the precision is now low within our estimates because we've been able to capture all of the data. So the precision depends on the variability, but not just the variability. It's a combination of the variability and the sample size and the proportion of the population that we have been capturing. Sorry, if we go back to something which actually has some error bars around it. One of the key things which gets calculated to be able to give you this confidence interval, and a number that again you see quite a lot of the time, is something called the standard error. So with, let's go for age, because this is a case where it's true. For age, each of these confidence intervals is approximately 2 times the standard error. The standard error is, in this case, the standard deviation divided by the square root of the sample size. When you have, again, a well-behaved variable, like in this case, age is nice and symmetrical, it looks a little bit like a normal distribution in the histogram. In those cases, the standard error can be calculated as the standard deviation divided by the square root of n. And you can get the confidence interval by adding plus or minus 2 times the standard error. Unlike the standard deviation, the standard error decreases with the sample size, again, regardless of how it works. The larger the sample size, the smaller the standard error. The larger the sample size, the smaller the confidence interval, the narrower the confidence interval gets. So when we present our results, we want to be presenting all of this information. All of it is relevant. What was our sample size? What's our estimate? The standard deviation and the standard error are not the same thing. They tell us two different things. The standard deviation is telling us the variability in the data. The standard error is telling us the level of precision in our estimate. And then the confidence interval is a way of making that standard error easier to interpret by giving us a range of values in which we think the real estimate of average age lives. This confidence interval does not tell us much, if anything, about the variability in our data. Again, that's a sort of common misconception that sometimes people use confidence intervals to express variability, which is not what they do. They represent the precision in our estimates and the range of values in which we think our average or our percentage, if we're looking at gender, might be lying within. So let me go back. Just to recap a couple of these concepts, and then I will open it up for questions before the final push. When we talk about variability, this is when we're talking about the underlying differences within our population. We're talking about looking at the spread, we're looking at the distribution in a histogram or a box plot, or we're calculating a standard deviation, or we're looking at an interquartile range, or we're looking at some way of expressing how different people are different within our data, or different study units are different if you're looking at fish rather than people. The variability is not dependent on the sample size. As the sample size increases, the variability will remain approximately the same. We might get a bit more variability in a larger sample size just because we've got a bit more data. So we might have extreme values popping up more commonly in a larger sample size. But in general, the variability is approximately the same regardless of sample size. Our precision is the uncertainty in our estimate based on the sampling methodology. And as the sample size increases, the precision in our estimate also increases. So standard error is dependent on sample size, standard deviation is not. The first example I gave you is what we would call a census, where I have all 1,000 farmers represented within the dataset. And the second case is what we call a sample. A subset of possible survey units were represented within the data. Estimates from both censuses and samples need to be presented along with some kind of measures or displays of variability. And if you've done a sample, we need to be dealing with some kind of measures of precision to express the uncertainty which arises as a result of our sampling methodology. Let's just talk a little bit more about some statistics here. When we're talking about the standard deviation, I meant to go to this slide before, we're talking about the measure of the variability in the data. There is this other kind of interval that we can deal with called a prediction interval instead of a confidence interval. And I kind of alluded to that earlier because this is approximately the mean plus or minus 2 times the standard deviation sometimes. If you have a nice distribution like we had with age before, that formula will more or less give you the 95% prediction interval. And what that means is if 100 new observations from my population were to appear, 95 out of those 100 I would expect to be within that particular interval. The standard error is a measure of the variability in the estimate, not in the data itself. So it's a measure of uncertainty, it's a measure of margin of error. All of these mean effectively the same thing. And our 95% confidence interval is if we were to do the same sampling process 100 times, 95 out of 100 of the means or the estimates from those samples would be within those intervals. And the formula is approximately the mean plus or minus 2 times the standard error. Again, sometimes. And we'll come on to some of the times when it's not like that in a minute. As a little aside, let's just, instead of thinking about precision against variability, let's flip the question a little bit and think about the concept of precision versus accuracy, because there's something that's sort of missing from our confidence intervals, which is quite easy to overlook. So I'm just going to keep making some more words appear. And we've got words like precise, accurate, reliable, valid, exact, unbiased. Potentially, these are all words which you're seeing which mean, this is good. This is a good estimate. This is a good process. Hopefully, or maybe not, you might be seeing that all of these words mean the same thing. They don't. They fit nicely into 2 categories. So precision and reliability and exactness all fit into 1 category. Accuracy and validity and unbiasedness all fit into a completely separate category. All 6 words on there are things that we should be striving for. We want something that is precise, reliable, accurate, valid, unbiased. Maybe not exact. Exact might mean we spent too much money, but it's still a good thing if we get the exact result. But we can be precise without being accurate, and we can be accurate without being precise. So what's the difference? You often see when people explain this, you've got these kind of targets like this. Something is precise if we consistently get the same result over and over and over again. So in the top left of my little shooting board, I am always hitting the bullseye because I'm being precise and accurate. And accurate means I am getting something which is correct. I'm getting something which is the right answer, or the answer which is the most real answer in the concept of a survey. But I can be precise and inaccurate if I am consistently getting the wrong answer. I can be imprecise but accurate if I am approximately getting the right answer, but never quite being sure where I am. I've got a lot of variability in my guesses. And I can be imprecise and inaccurate if there's a lot of variability in my guesses and I am still consistently getting the wrong answer by doing it. The worst possible scenario out of these four is not being imprecise and inaccurate. It's being precise but inaccurate. Because in this case, if we are consistently getting something that is incorrect, we are very sure about something which is the wrong answer. If we're precise and accurate, we're very sure about getting the right answer. This is good. If we're imprecise but accurate, we're getting the right answer, but we're not quite sure. So we might do a bit more research, we might do a bit more investigation. Here, we're getting the wrong answer, but we're also still, we're not really sure. We're not very confident in our wrong answer. So we're not going to make any big conclusions or sweeping statements based on this. Where we might, if we have been doing something which is inaccurate but precise. So it is better to be accurate and imprecise than it is to be precise but inaccurate, which often confuses people and scares people. But the reason why I'm saying this is that sample size and sampling methodology and the numbers which are expressed within the confidence interval, these all go towards the concept of precision and precision only. In most surveys, precision is almost entirely a function of the sample size. There's a little bit in there of the sampling methodology, which I'll come on to in a minute. Occasionally, you've got an aspect of precision based on the quality of your measuring device. So, for example, if you are measuring how long it takes for a respondent to complete a task, if I am using a stopwatch, that's going to give me quite a precise estimate. If I am using a sundial, that will give me an accurate measurement of time. It just won't be very precise. Both are tools which can measure time. One of them is more precise than another. Not usually that extreme of the difference between a stopwatch and a sundial, but they're the two examples that I like. What is not captured in the confidence interval is all of the things which go into the accuracy of the thing that we are estimating. So that also depends on the sampling methodology. Are we able to get a representative or random sample of our population of interest? In the example I was just running, the computer is told to always take a random sample. So all of the formulae about getting it 95% of the time within the estimate within 95% of the confidence intervals, that will work out because the computer can take a random sample. In reality, we often can't take a random sample. So we have to think about whether it is reasonable for the sampling methodology we have used to be giving us a sample which is in some way representative of our population, or is there bias creeping into it? Also things related to data entry procedures. If we're typing in and making mistakes, if we have a badly processed ODK form or digital data form. Also to do with the quality of the measuring device. And this is particularly in terms of questionnaire design. Are we asking the right questions to be able to get the data that we want? In my case, when I'm looking at sales income from oranges, my shady orange farmer, my shady orange baron who's running his organization probably has a very good estimate of sales income because he is the person who is buying the oranges. So he's probably keeping a record of every time he's buying the orange, how much is he buying it for? If you are doing a survey and asking someone on the spot, how much money did you make selling oranges last year? You've got recall bias. Will they be able to remember it particularly well? You've got issues to do with whether they actually want to tell you that information, because it could be sensitive information related to income. You could be asking the member of the household who's not responsible for money, so they're guessing. There's all kinds of intrinsic problems with measuring income, among other variables, through straightforward question answer type approach. And there's lots of other ways you can mess up your survey by asking leading questions or over interpreting the results of questions. And related to that, training enumerators, making sure things are translated correctly, timing the surveys. If you're starting the survey in January and finishing in June, perhaps you're not going to be getting a consistent estimate because in January in one place is different to June in another place. And accuracy doesn't matter if you're dealing with a sample or a census. All of these issues, to some extent, are very important. And none of these issues are captured within a confidence interval. So when we say we are 95% confident that the mean lies within this range of values, that is based on the assumption that the thing that we are measuring is sensible. So we have to make sure we design our methodology so that when we present estimates and confidence intervals, they can be interpreted meaningfully and not taken out, not representative of something which is not a useful number and not the number that we actually want to be looking at. And mostly the precision box is what we were talking about in this webinar up until now. A lot of those issues to do with accuracy came up when you were listening to Alex and Carlos over the last 2 weeks. Maybe some more of them will come up in the future as well. Let's talk a little bit now about sampling methodology and the relationship of sampling methodology with estimation. Because again, when I was presenting those results earlier, that was assuming we could just take 100 farmers from my 1,000 farmers and have no issues with speaking to those 100 farmers. In that case, that could have been true, but in reality, we often don't go through that process. We often do what we call clustered sampling instead of simple random sampling. So what we mean by cluster sampling is we go to 10 villages out of the possible 100 villages, and within each of those 10 villages, we speak to 10 farmers. Instead of taking the list of all 1,000 farmers, oh, we had different numbers. I was close. Instead of taking our list of 1,000 farmers and just randomly picking 100 out of them. So yeah, in my orange growing organization, there were 50 villages, and in each village, there are exactly 20 farmers. I have an incredibly well-organized orange growing organization, which is based around everything being a nice round number. So in a clustered sample, we would randomly pick 10 villages to go to and randomly sample 10 farmers within those villages. Within a simple random sample, we just pick 100 from the whole list of 1,000 farmers. Each of those methodologies would give a different estimate for our standard error and for our confidence interval. Because with the clustered sampling approach, we don't have as representative a sample as our simple random sample. If we take this to the absolute extreme and say that, okay, we've actually got all 100 of my farmers came from one village. So I run, instead of there being 50 villages with 20 farmers in each village, let's say there are 10 villages, each with 100 farmers. I can randomly select one village and then speak to all 100 farmers in there. But that is not as particularly good representative sample of my whole population, because I've only seen one village. And I don't really know if the results in that village are going to be the same as in another village, and if that village is going to be the same as in another village. So anything other than a simple random sample increases the standard error. It increases a lot if we do something really stupid, like the example I just gave. It increases not quite so much if we do something relatively sensible, like speak to 10 farmers from 10 villages. But the extent to which it's important depends mostly on how different the villages are to each other. So if it turns out that village 1 and village 2 and village 3, or cluster 1 and cluster 2 and cluster 3, results are the same more or less in each of those villages, taking this different process doesn't really affect our standard error. If they were all really different from each other, then that means we'd get a very different result depending on which villages we went to, and this increases our standard error. There's also an element here which is how many individuals are sampled per village, per cluster. If all of our villages are really, really different, but we only take a small number from each village and we go to a lot of villages, that's still quite a good representative sample. So we can mitigate that problem of having very, very different villages by making sure we speak to a lot of different villages. So e.g., a farmer with 5 villages, a sample of 5 villages with 20 farmers in each will have a larger standard error than a sample of 20 villages with 5 farmers in each. The formulae by which these all get derived are quite complicated statistically. It's called calculating a design effect, or DEFF. This is somewhere where your software of choice, your statistical software of choice, can help you in calculating that number. The formulae for standard error and standard deviation, all of these things, if you really want to, you can calculate them all by hand if you wanted to. When you start getting to adjusting your confidence intervals for your sampling methodology and calculating design effects and calculating your intra-cluster correlation coefficients, which is a subcomponent of your design effect, these are all things which you don't need to know how to work out the formula, because it's incredibly complicated statistical formula which go on for days. But if you press the right buttons in your statistical software, it will do it, and it will adjust your standard errors, and it will adjust your confidence intervals according to your sample design. So this is possible if you're doing SPSS or Stata or R. This is not possible if you are using Excel, or I don't think it's possible in Minitab. I don't think it's possible in lots of other stats packages. So if you're using a good stats package, this can all be done to help make sure that you are not getting estimates of precision which are too low. You're underestimating your precision. You're getting narrower confidence intervals than you'd expect because you're not taking into account your sampling methodology. Okay, final topic of the day, which is going to lead into the next webinar as well, which is when I am looking at my data so far, I probably don't just want to pull out some statistics. Okay, how many men, how many women, what's the average age, what's the average income, how many went on training, and so on. I probably want to compare or look at, okay, how are my male farmers doing in relation to my female farmers? What's the average income of my female farmers? What's the average income of my male farmers? Who's attending training more, the male farmers or the female farmers? Is the training being beneficial? Are the farmers who are attending the training getting higher incomes than the farmers who are not attending the training? So this is where we start to think about the concept of disaggregation, which is a long word that I sort of hate. But it means when we're looking at subgroups of our data. And so the answer is, sorry, I haven't put the question on, can I disaggregate my data by gender? The answer is always yes, you can. The more important question rather than can is should I disaggregate my data by gender, which I'll come on to in a second. So let's stick with a sample size of 100. And let's go to my little disaggregation tab. There we go. So I am going to disaggregate by gender. I am going to look at age. And I would like to know, okay, what is the average age of male farmers and female farmers? So you can see in this time around, I got 38 male farmers, 62 female farmers. The average age of my male farmers was 44. The average age of my female farmers was 44. I've got calculations of standard deviation and standard error and a confidence interval for each, which I've got plotted here. We can see from this sample, the average age looks quite similar. The value of the standard deviation looks quite similar. The value of the confidence intervals looks quite similar. It looks like we've got similar age with similar average age and variability in age for our male and our female farmers. I can do it again. Oh, this time, now it's a little bit different. Now, oh, my average age of female farmers is a bit lower than the average age of my male farmers. This time it's 42 versus 45. Again, standard deviation looks quite similar. Oh, so now maybe I'm thinking that my male farmers are a little bit older. And I can do it again. Again, this time the female farmers are a little bit younger. Do it again. Oh, they're even younger this time. Oh, so there's maybe a bit more volatility in our estimates when we are starting to disaggregate, particularly because if you think about our sample size, we no longer have a sample size of 100. We have one sample size of 33, and we have a second sample size of 67. So when we were thinking before about the precision in our estimates, let's go back to our confidence interval. And actually, this is telling us not that the average age of the male farmers is 48, but the average age of the male farmers is somewhere between 44 and 52. We're pretty confident it's somewhere between 44 and 52. We can see side by side, the confidence interval for the female farmers is much narrower. It's covering a smaller range of values because it's got effectively double the sample size in this particular instance. So when we are thinking about disaggregating our data, the first thing we need to think about is, do we have a sufficiently large sample size within each of the groups that we want to be looking at to get reliable, meaningful, precise, whatever word you want to use, estimates of whatever it is that we want to look at. It's even worse if I switch here to training. So if you remember from earlier, the majority of the farmers in this particular case attended the training session. So in this particular sample of 181 did and 19 didn't. Because only 19 farmers are in my no training group, I have quite a wide confidence interval for where the average age is, 40 to 48. That doesn't look too bad, but that's because age isn't so variable. Let's make it gender instead. What percentage of the group who had no training were female? Now we can see that confidence interval goes from somewhere between 40% female farmers in the no training group up to 84% of female farmers in the no training group. So that estimate of, okay, within our group of farmers who didn't attend training, what's the breakdown between male and female? The answer is, we don't know, because we don't have a large enough sample. Our estimate is 63%, but in reality, could be quite small, could be really, really high. So effectively, we need to consider this when we come up with our sampling process. So when we are designing our survey, we can use what we call stratified sampling to make sure that we represent all the groups that we want to have represented. We have to think about beforehand, am I going to want to disaggregate my data? If so, should I specifically target people in subgroups which I expect to be small? If I know that not many farmers attended the training session, not many farmers didn't attend the training session, and I am able to get a list of who are those farmers who did not attend the training session, I can have one sampling scheme for those farmers and get a sample of 100 farmers who didn't attend the training, and then get a separate sample of 100 farmers who did attend the training. We can go from that unbalanced sample, and we can use what we call statistical weighting to then get back to estimates of the overall population and combine them back together if we wanted to. And we have enough data within each group to get good estimates within each group. If we don't have the large enough sample here, in this case, we can't really do anything meaningful within this subgroup. All we can do is use the population estimate for overall what's the difference between male and female. Because this range of values from 42 to 84, this is too much imprecision to be a useful number to be working with. So this consideration of, can I disaggregate my data? The answer is yes. But should I disaggregate my data? Start considering if you have enough data, or think about it before you design the sampling methodology, especially if you know there are going to be groups with low sample sizes or groups which are rare occurrences in the real world, whatever that might mean for your particular context. One final point before I open this up for questions. Let's increase, let's go to back to gender and go to income, because I like income. Okay, so let's think about what we can see when we're comparing these side by side. We have got for male farmers here an estimate of average income, mean income, which is 15,000, an estimate for female farmers, which is only 9,500. This is quite a large difference between the male farmers and the female farmers. The income in the male farmers on average is about 50% higher than the average in the female farmers. When we look at these confidence intervals, these estimates in these confidence intervals side by side, we see that the uncertainty within here means that, okay, within the male farmers, the lowest we think the real average is could be down to about 10,000. With the female farmers, we think the highest it could be up to about 12,000. The top of this limit overlaps with the bottom of this limit here. So if we're looking at these error bars side by side, the common misconception to make at this point would be to say that because the error bars overlap, that means there is no difference between male and females in the average income. What I just said was completely incorrect. When we have this case here where there's a bit of overlap between the top of a confidence interval, when it's a 95% confidence interval limit, and the bottom of a 95% confidence interval limit like this, in this particular scenario, we can't conclude whether there is a significant difference between income for male farmers and female farmers, when it's in this case where there's just a little bit of overlap like this. If I were to increase my sample size to 500, now we can see that the highest we think our estimate for female farmers is all the way down to only 9,600. The lowest we think our estimate for male farmers is about 10,800. So this is about 1,000 units higher. The lower limit here is about 1,000 units higher than the upper limit here. Where we have non-overlapping confidence intervals, so here there's no overlap at all between the males and the females. In this case, we can conclude that there is a significant difference between male farmers and female farmers in the average income. So where we have no overlap, we can conclude that there is a significant difference between the two. But where we have overlap, the reverse is not true. I have to do it. There we go. This is not enough to say that there is no significant difference between the two. This is a case where we don't know, where we need to do some more testing. If I change the variable quickly to age rather than gender, in this case, we can conclude that there is no significant difference in the average age between males and females. Because in this case, the estimate itself is within the confidence intervals. So here, the estimate for female farmers, not just the upper or lower limit, is within the range that we have for female farmers. So when the estimate itself is within the confidence interval limits, then we can conclude that there is no significant difference in the average age between males and females. When they completely do not overlap, so when they're completely separate, like this, then we can conclude that there is a significant difference. But it's cases like this where we have a little bit of overlap, where we just can't say either way. So these confidence interval limits, when we present them side by side for two different groups, they can help us to determine, are we seeing differences which we would clarify as statistically significant. And this is leading in to the concept of hypothesis testing and p-values and all of this. Confidence intervals and p-values are very, very strongly interrelated. And that is something which is going to be covered in the next webinar. So we won't be talking about that in more detail today, but these particular limits are very useful for expressing the uncertainty, and they are indeed related to helping you determine whether you can say that male farmers are earning more than female farmers. And again, because we have better estimates when we have larger sample sizes, we have more precise estimates when we have larger sample sizes, we are more likely to be able to claim that we are seeing a real difference between the two. Even with age, which we've seen so far to be relatively similar between male farmers and female farmers. If I increase my sample size to be large enough, like here, I've now got a sample of 900 farmers. My confidence interval limits are very, very narrow. They now go from 44.97 to 45.72 for male farmers, 44.14 up to 44.65 for female farmers. These no longer overlap. So I can now conclude that female farmers are younger than male farmers. Is that a meaningful difference? That on average, male farmers are less than 1 year older than the female farmers in my orange growing organization? I would say caring about that particular difference is not of interest to me. Whereas caring about the difference in income, which appears with a much smaller sample size, and where the difference is not less than 1 year, the difference is around 4,000 or 5,000 units of income. This one is a much more interesting difference to be able to detect. So again, there's always this trade-off when we are designing surveys and designing samples of getting estimates which are unnecessarily precise. We can be wasting money collecting more and more and more data, when in reality, getting that extra data is not really helping us too much. It's just wasting our budget rather than actually telling us more useful information. We need to get the balance right between having a large enough sample size to have good estimates of what we want, but at the same time, making a sensible allocation of our resources. Okay, I think that's more or less everything I want to say. Let me just go and finish my recap. So if we want estimates by subgroups of our population, if we want to disaggregate our data, we need to make sure we've got sufficiently large sample sizes and think about it beforehand. Consider using a stratified sampling scheme, considering having a separate sampling scheme for trained farmers and untrained farmers, or female farmers and male farmers, if you know that the main objective of the survey is going to be to compare or to pull out estimates within each of these groups. Okay, overall recap of what I've talked about for the past hour or so. Make sure you don't shy away from the variability in your data. A lot of people tend to just present averages and maybe confidence intervals, and if you're lucky, a standard deviation. That's very hard to be able to actually understand the variability in your data. Variability is good, I find. It helps explain what's going on. Just a simple average alone doesn't explain things particularly well. So use lots of graphs to show variability, use histograms and use box plots to show your variability. Don't just present 100 different summary statistics for variability, because they get incredibly confusing and incredibly difficult to understand what's actually going on. Oh, going backwards rather than forwards. If you are using a sample, if you do not have a census, if you are not speaking to the whole of the population in which you are studying, you always present some kind of measures of precision along with your estimates. I haven't gone into all of the formulae for calculating confidence intervals, because it depends on a lot of different factors. It depends on whether you're dealing with a variable like age, which is approximately normally distributed, a variable like income, which has a skewed distribution, a variable like gender, which is a binary male or female. You can get a variable which has multiple categories, which has what variety of orange they were growing. Maybe there's 5 different varieties of orange, and an estimate for each of them. All of those have a different formulae attached to them for calculating a confidence interval and for calculating a standard error. If you are using a good statistical software package, they will do all of these calculations and all of these formulae for you. And if you're using a very good stats package and you're able to use it well, you can calculate those with respect to your sampling methodology if you have a clustered sample instead of a simple random sample. So if you really want to calculate these things by hand, you can, and you can dive into lots of lovely YouTube videos and lots of lovely papers online about how to do all of these formulae and all of these calculations, but you really don't need to. You just need to know what the confidence interval means, what the standard error means, why it's important, and be able to present that along with your data. And final point, if you want to disaggregate your data, make sure you've considered if you have a large enough sample size, and think about that ideally before you collect the data. Know how you are going to want to disaggregate the results, whether it's by gender, whether it's by district, whether it's by country, whether it's by whether they followed the guidelines or didn't follow the guidelines, and so on. If you are able to do a stratified sample and your key objective is going to be looking at different subgroups, do this in advance, because it will make your life a lot easier when you come to do your analysis at the end. I'm just going to put up a page of references and resources to go into more detail. If you want to play along yourself with the example that I've been going back to, that's a little thing that you can click on that web link or go to that web link, and you can play along at home and do lots of samples and see how everything varies by trying that. So any questions, comments, topics that people want to bring up? Yes, Cynthia.
Hi there. I just wanted to first say thank you so much for that. That was very, very rich, and I think very, very useful for folks who are working on the gender and breeding, but also much more broadly. I particularly wanted to say how much I appreciated your flagging the difference between precision and precision and accuracy.
Okay.
That's something that really trips people up a lot when we're looking at quantitative analysis of gender issues such as empowerment or decision making. So I was really, really happy to see you flag that, and I'm hoping that's something we can continue to pick up and wrestle with along the way. And last but not least, I just wanted to say, great question in terms of, are the slides available? And I'll make sure that we circulate access to the slides, but also recording of each of the webinars as soon as we can to all of the scientists who are in the gender and breeding postdoc initiative, and also through to the WorldFish scientists as well, and then pass those on freely to anyone who's interested.
Perfect. Thanks, Cynthia. Okay, in which case I think we are done, unless there are any very, very final thoughts. We can wrap up on time and let you get back to your morning or evening or afternoon, depending on which part of the world you're joining us from.